Okay, so now let's graph those two electric field functions. So we have a function for inside. Okay, so this was inside. And we had a function for outside. Okay, so let's graph E versus R. So A is an important place on my graph. Agree? A is the radius. So what does the function look like? It is E is equal to QR over 4 pi epsilon naught times A cubed, I think, inside. So, all right, so Q, 4 pi epsilon naught, and A cubed are all constants. So what would this graph look like between 0 and A? A straight line increasing, right? Now outside, we determined that it behaved just like a point charge at the center, which gave us Q over 4 pi epsilon naught times R squared. So what's going to happen to our electric field after we pass this point A? It's going to fall off like that. What do you think? Graphing them is important. What's up? Okay, so a line of positive charge. So let's pretend like that's our line of positive charge. And it's infinite, so it goes up and up and up forever and down and down and down forever, but I can't draw up and up and up forever and down and down and down forever. But we're looking at a point out here, a distance r. Okay, so for a sphere, we made a Gaussian surface that was symmetrical to that sphere. Now we have a line of charge. What shape could be symmetrical and surround that line? Remember, line goes on forever and ever and ever. A cylinder. So now we're going to make a Gaussian surface in the shape of a cylinder. So again, it goes on forever and ever, and I'm not the best at drawing stuff these days. So there's our Gaussian surface cylinder with a radius of r, because I want to find the electric field at that point. And so that would be the area, the little dA, okay, that our electric field is passing through. So the electric field, now remember, there would be an electric field to this piece, electric field due to that piece. Remember when we did a line before, and we had all those electric fields, and the in this case the y components would cancel out, and you only have the x component. All right, so you start with Gauss's law, and Gauss's law states that the charge enclosed by our Gaussian surface over epsilon naught is equal to the closed surface integral of the electric field, dotted with the area bit that is perpendicular to the electric field. Okay, so now the charge enclosed, now this is a little bit interesting because our charge enclosed, lambda would be, remember, the charge per length, and wouldn't the charge per, I'll use big L, the length of our infinitely long line of charge, there we go. So the charge enclosed could be lambda L. So I can substitute and say that the charge enclosed is the linear density times this infinite length. Okay, if it had a finite length, then we could substitute that in there too. Okay, so then that gives us lambda L over epsilon naught is equal to, now again, isn't my electric field perpendicular to the area? So my dot product is just going to be the product of the electric field times the surface area. So we don't have electric field shooting out of the top of this cylinder or the bottom of this cylinder. We just have the sides. Does anybody remember how to find the surface area of a cylinder? The circumference, 2 pi r times L. So it looks like I can divide by L on both sides, and we'll get an electric field that's equal to